FFTs and digital filtering. What's not to like? In my first video looking at digital filtering, I started with my basic FM broadcast receiver, saying that what I was going to explain was this particular block here, the low-pass filter block. That particular block was actually this one, the FFT low-pass filter. I said I would explain the low-pass filter in the first one and then the FFT part in this video. Well, it's now time for this video. When you're looking at how you actually implement a filter, specifically FIR or FIR filters, you could implement them either in the time domain or in the frequency domain. What I showed in my first video was this. This is in the time domain. This is where you have a bunch of delays and multiplies and adds, and you're using them all together to create convolution in the time domain. What we're going to be talking about today is the FFT part, where you're doing it in the frequency domain. The reason that this works is that first F in FFT, the fast part, the fact that you can do it very, very, very efficiently. That's what makes the FFT low-pass filter not only usable, but it actually works better in a lot of cases than in the time domain. Let me explain how you can see that. What I've created is this really basic flow graph. And this particular flow graph, all I'm using is I've got a null source because I don't care about the output. All I'm going to be doing is measuring speed relative between a normal FIR filter, these types, this decimating FIR filter actually operates in the time domain, and an FFT filter, which is operating in the frequency domain. What you're going to see is you're not going to see anything displayed when I run this. Instead, you're going to be looking at the data down here in the lower left-hand corner. Running this, what it starts out with, as I'm running it, you can see in the lower right-hand corner here, it says, the rate now, and it's about 34-ish, 34.5-ish megasamples per second. Now, I'm going to disable the time domain version and implement the FFT version. And again, I'm using the exact same impulse response, the exact same filter taps for both. So this is really an apples to apples comparison. When I run this and it starts going, I'm getting, instead of 35-ish, I'm getting almost 350 megasamples per second. So over a 10 times increase in speed between the frequency domain and the time domain. That gives you an idea of the efficiency. That said, it's not straightforward how you actually implement this particular type of filter. Again, with the time domain version, what you have is you just have a bunch of delays and multiply constants and throw them onto an add, and as the Brits would say, Bob's your uncle, and you're done. If you try to do straightforward filtering in the frequency domain, it doesn't work out as well. Let me explain what I mean by that. This is I recognize that this is a very complicated looking flow graph, and the reason being is I'm trying to do comparisons between different aspects of it. The important part is down here on the bottom. Instead of using an RTL SDR this time, I'm actually using just a file source so that when I hit go, it goes much faster and I don't have to wait for the RTL SDR to get booted up. And what we have here is on the bottom, I have think of this as my radio. And now I'm coming through, I'm creating my time record, I'm going through an FFT. Now, the reason that the FFT works is due to the fact that convolution in the time domain is equivalent to multiplication in the frequency domain. And therefore, what I'm going to be doing here is I'm creating the FFT, and then I am multiplying it by the spectrum that I want to create. And I'm doing this in kind of the cheat method, meaning that all I'm doing is I'm creating this spectrum just by saying, okay, all of the frequency bins that I don't want to pass set to 0, multiply by 0. All the ones I do want to pass, multiply by 1. And I'll show you that here in just a second. And then the rest is just showing different comparisons for that. So for example, this part here, I'm actually doing a comparison of my signal, showing the impulse response of the signal, plus then I also have a comparison for the, so you can actually see the actual spectrum as I originally envisioned it. And running this, what you start out with, this is what I'm talking about. I'm looking at it in the spectrum. I'm saying, okay, anything in my stop band, that's a 0. Anything in my pass band is a 1. And you notice there's really no transition band. And when I look at the spectrum, I'm thinking, wow, that looks actually pretty good. This is my original spectrum here in black. This is my filter overlay. And then this is what my filtered spectrum looks like. And if I get rid of everything else, yeah, that looks pretty good, doesn't it? And then when I look in the time domain, yeah, that still looks actually pretty good, except you can kind of notice every now and then you see something kind of popping up on the top there, which that really shouldn't be with FM. And you really actually see it better in the constellation. With FM, a constellation should be a nice, pretty donut. And what is all this crap here in the center? And what that is that is actually aliasing. This is called time domain aliasing. And the problem here is that, yeah, I can kind of sort of, even my baseband spectrum looks decent, but notice here on the right-hand side that all that black stuff is jumping up. Well, that's due to the time domain aliasing that I was talking about. And the reason for that is that when I am actually filtering a signal, I'm smearing it out in time. And to demonstrate that, I'm going to yet another flow graph. What I have here is I have my signal, and I'm splitting it into 2 parts. I'm essentially only bringing in half of the samples at a time, and then the other half are just becoming zeros. That's what I'm using this null source for. And when I run this, what you see is, you see that this is my unfiltered signal, and this is the part that I'm bringing in, and then the rest is zeros, and then the other part is the filtered part. Notice that the filtered part actually has some ringing, it looks like ringing on either end. That is due to the impulse response of the filter smearing it out in time. And when I'm coming back to here, what's happening is that I'm not allowing for that smearing in time, that time domain aliasing. And therefore, I'm getting all kinds of glitches and other things that are essentially going wrong with my signal, and it's not the right way to do it. So you would think, okay, what is the right way to do it? Well, let me add in a little bit of a buffer time. And what I'm doing here is I am pulling in a certain number of samples, and I'm allowing for the impulse response of my filter to be accounted for. So I'm pulling in this case, I'm doing 1,024 samples. My filter length is 501, which is actually a very long sample length or impulse length. And I'm saying 1,024 minus 501 is 523, and that's how many samples I'm pulling in at a time. And when I run this, what it's going to do is it's going to pull in that number of samples, and then it's going to do the filtering, and then on the back end, it's going to just pull out those 523 actual samples. And this is what it looks like in the frequency domain, which is still not right. So the blue is what I just created trying to do that frequency sampling. Or not frequency sampling, the filtering in the frequency domain. By the way, if you try to set it up where you just say, hey, do an FFT, multiply these bins by this amount, there's a term for that. That's called a frequency sampling filter. It's possible to do it that way, but it's very niche, and you have to design it very carefully for, I think, hopefully you're seeing all the reasons why. Whereas, so this is what it looks like trying to do it the way I just discussed, where I bring in 523, I have 501 essentially zeros. It gets filtered, and then I'm just pulling those 523 samples back out and then just tacking them onto the end of each other. This is what it looks like. Going over here, you can kind of see, let me pause this for a second. What you're seeing is you see these little impulses. That is where the records are coming together between contiguous FFTs. And that's what's creating all of those impulses. That's what's creating this really bad looking spectrum. If you try to understand how I feel about this type of spectrum, well, I'm just going to say that this spectrum is definitely not Scottish because it's crap. And if you want to understand what the heck I mean by that, where that phrase comes from, there's a link in the description down below. When you're looking at this particular type, this is not how to do it right. Instead, what we're going to do is we're going to do a filtering where we're going to bring in the samples in the record, and that's what we're going to do here. We're still going to split it. We're still going to allow for each record to be half essentially samples of the that we want to filter, and the other half is zeros. That will give us plenty of time, or allow for the impulse response, the smearing in time. And then at the end, we're not going to just pull out the samples between each record. We're going to overlap them and then just add them together. And it turns out that mathematically, allowing that to happen, the impulse responses will then cancel each other out, and you end up with a nice, perfect signal. This particular one that I've implemented here is called the overlap and add method. There's actually two different methods that you can use in the frequency domain for filtering. One is called overlap and add. That's what I'm going to demonstrate here. The other one is called overlap and save, also called overlap and scrap. And the way that works is you have the overlapping time records such that you basically pull out samples from the previous record equivalent to the impulse, roughly the length of the impulse response of your filter, and then after the filtering, you just throw those away, and by allowing each one to continuously just keep overlapping them like that, and then throwing them away, and then just putting the final sample stream together with the samples that are left over, you once again wind up with a really good, with a perfectly filtered signal. And I'm told that is actually a more efficient method than the overlap and adds, the way most people do it. It's probably the way they do it in GNU Radio. Unfortunately, I can't figure out how to do overlap and save with the GNU Radio flow graph, but I can demonstrate the overlap and add. What we're going to be doing here is we're going to be looking at the signal, and what I'm going to do is I'm splitting it into two streams, and each stream I'm doing a zero padding, so you have 1,024 points in this particular case record. You're going to do 512 samples of the signal and then 512 zeros. Goes through, gets created into a time record, goes through the FFT to put it into the frequency domain. You're doing a multiplication in order to multiply it by the FFT of your impulse response. Another reason why this is so efficient is that I can actually pre-calculate, and that's what I've done here. I can pre-calculate the FFT of my filter, so it's just sitting in memory, which means that I don't have to constantly keep recalculating it over and over again. It's done. And so now I've got the multiplication occurs, convert it back into the time domain, and then at the very end, what I'm going to do is on one of them, I've added in this delay of half a record, and then I just add them together. And once I do that, everything overlaps really nicely. The impulse responses cancel each other out such a way that it makes a nice, perfectly smooth signal. And when you run this particular filter, what you wind up with is this is looking at three different signals. First off, let's start with the top branch, and let me explain that this is the top branch here. This would be branch A, this would be branch 2 or branch B. And so with that, what I wind up with is this is what it looks like, and you can see the ringing on either end due to the impulse response of the filter. And then I'm doing the exact same thing with branch B, but notice that it's offset from the other one, and when I turn them all on, I wind up with the perfectly smooth signal, and that is this part here. There's my perfectly smooth signal. Here is the spectrum comparison between the different ones. And what I'm doing as far as different ones is concerned is you're looking at this, the one that I created using the branch A, branch B, and adding everything together. That's this one. And notice that it has a nice, good transition width. The stop band is really low. The reason being is that this is the specific window that I used on this one was a Blackman Harris, which has 92 dB of stop band loss. I mean, it's a humongous amount. And then I compare it to a normal GNU Radio FFT filter. That's what this is, the red is. And then I'm also doing a comparison with a normal time domain. That's this one in green. And notice that they pretty much all are exactly the same. You see a little bit down here. That could very well be due to the fact that the math behind each of them is just different enough that you're going to see slight differences, especially down here at the very bottom end of the scale. But that is, in a nutshell, that is how when you look at an FFT filter, that means that you are implementing an FIR, a finite impulse response filter, in the frequency domain, not in the time domain. And depending on the number of samples, and I hear so many different numbers bantied about it, there is a certain point where the number of taps in your FIR filter gets to beyond that point, it's more efficient to use the FFT. And that number is anywhere from, depending on who you talk to, I've heard from 16 up to 50, meaning that if you have a impulse response that is at least 50 taps or more, you're much more efficient using the FFT filter than you are using the time domain filter. And therefore, that's the difference between those two. Therefore, when you are looking to put in a filter, you might be just putting in like a decimating FIR filter, or you might be putting in just a low pass filter or a high pass filter or a band pass filter. Again, the low pass, high pass, band pass is a separate part from how it is actually implemented. Again, you can implement those either in time domain or the frequency domain. Because again, it has to do with the fact that convolution in the time domain is equivalent to multiplication in the frequency domain. There you are. That is the quick and dirty on the purpose of the FFT filter. Again, I've left all of these flow graphs on my GitHub, link in the description. Please feel free to download them, play around with them, modify them, mutilate them, spin, fold, all the necessary things that you need to do. Any questions, comments, leave them in the comments below, and I will see you next time.